Hello everyone, today we will be talking about how to do graph learning with the PyTorch Geometric package. My name's Joshua and I have done some undergraduate research on graph learning using this package. Today I will share with you some of the tips and how to get started with doing some kind of graph learning using PyTorch Geometric. And in this video I will show you two applications of using PyTorch Geometric to perform some basic machine learning tasks. In this video, I will not talk about the theories of graph learning, and you can feel free to look that up in the internet. Instead, I will focus on how to write the PyTorch code and how to do the applications. How do we design our graph neural network? So let's get started. Make sure that you have PyTorch and PyTorch Geometric installed in your computer. You can use any methods that you would like, for example, pip or anaconda. Next, we will start a new notebook, and first of all, I will show you how does PyTorch Geometric store the graph data. Let's take a look at the documentation to see what kind of data does each graph contain. As you can see here, we have a matrix containing the features of every node. We have a graph connectivity in a special format that I will demonstrate to you later, and it is called edge_index. Next, the edge features, for example, the weights, or if you have multiple weights for every edge, they can be stored in the edge_attribute matrix. Also, the target to train against will be called data.y, and this kind of target values can be very flexible in terms of its shape, depending on whether your task is performing, for example, classification for every node, for every edge, or for the entire graph itself. Also, the graph data can contain a position matrix, which would be useful for some applications related to point clouds, but we will not touch on that in this video. Next, let's try to implement this for some real kinds of situation. Let's say here we have 4 people, perhaps on some kind of social network. For every node, we will have the age and income level of that person. And for every 2 people, if they know each other, then there will be an edge between them. The target that we need to predict for each node is the hours that they work in our day job. And the weights of each edge would be the time that both of them have met each other. To implement this in PyTorch Geometric, we will need to use the data class to contain the information about the graph. Next, let's create a new data object. To do so, we would need to include all kinds of informations that the documentation have just mentioned. Some of the informations are optional, for example, like position and edge attribute. Let's first write the X matrix. This would mean the first person is 42 years old and make 1,200 of some random currency, and etc. Now for our edge index, the format of the edge index is less intuitive than we would want. According to the documentation, our edge index would be a matrix of 2 rows. The first row would write the source of every edge, and the second row would write the destination of every edge. Since we are working with an undirected graph here, we would need to include every edge twice. Now we would have 8 edges, or 4 undirected edge here. Next, we would include the edge attributes. The shape of our edge attribute is number of edges and then number of edge features. This setup corresponds to the fact that person 1 and 2 have met each other for 8 years. Person 2 and 3 have met each other for 7 years. Person 3 and 4 have met each other for 12 years, and person 2 and 4 have met each other for 3 years. We will also write our Y tensor. Now to combine all of our information, now let's take a look at our data object. It shows that X is an object with 4 points and each with 2 features. We have 8 edges, and every edge has 1 attribute, which we will call the weight. And we also have a target label containing only 1 variable. I also want to show you some of the instance methods that we could use for our graph object. For example, we can call data.numNodes to check the number of nodes, data.numEdges, whether it has isolated nodes, whether it has self-loops, or whether the graph is a directed graph or not. There are other instance and class methods that you can use, and they will be very helpful. Be sure to check the PyTorch Geometric documentation for more. Next, we will move to our first example, which is doing semi-supervised learning classification with the Cora dataset. The Cora dataset is a dataset containing some citation information for academic papers and articles, and the links or edges between the graph nodes, which are the articles, are the citation information between 2 papers. So by using what this paper has cited and what cites this paper, we are able to predict which category the paper belongs to. Semi-supervised learning refers to the task where we are dealing with one big graph here. All the information, all the nodes we have are contained in one graph. However, the machine does not have complete information about the whole graph. Instead, for some nodes and edges, it knows what information it contains, and for some nodes and edges, it doesn't know. So using the known edges, we need the graph learning network to be able to learn the pattern and predict what kinds of category the remaining unlabeled data belongs to. To do so, we need to first import the Cora dataset and also PyTorch. Let's take a look at our dataset object. Since we know that our data is one big graph, the dataset object does not contain useful information, but the first entry and the only entry of our dataset object contains the information that we need. We are going to move this into a new variable called data and put it on our GPU. We see that in our data there are 2,000 and something nodes and about 10,000 edges. And we also have 3 variables belonging to the data object called the training mask, validation mask, and the test mask. Let's take a look at the training mask. The training mask is actually a tensor or an array of Boolean values. When we pass the training data into the graph convolutional network, we want to mask some of the training data and only allow the graph convolutional network to access part of our graph. So by covering part of the graph, we can train our model to test if it is able to generalize to all of the graph. Next, we will write our graph convolutional network, and to do so, we will need to import GCNconv from the PyTorch Geometric package. For our graph convolutional network, we will perform graph convolution twice, and we will start with the number of node features that each node has, and then perform a convolution to obtain 16 hidden features. And then we will perform the convolution again to output another tensor that will be used to predict the class. To be sure, let's check how many features and how many classes we have for our dataset. Next, we need to define the forward pass logic for our graph convolutional network. Graph convolutions are very similar to neural networks or GNNs, and after every convolution, we need to remember to perform a ReLU, and that's just it. For our convolution step, it takes two inputs, which are x, the node features, and edge index, the connectivity matrix. And then, when we return x, we note that the range of the returned values are from -infinity to infinity, which means they are logits. After everything is done, we will now write our training loop. In every epoch, we will pass the graph data into our neural network, which will generate the predictions of the neural network. And then, when we calculate the loss, since we have a training mask, we will only use the nodes that are in the training mask to calculate the loss. This means that the model will only try to optimize for performing well towards those training data, and it makes sure that it will not try to use the validation and testing data for training as well. Now the training is done, let's evaluate our model on the testing data to see if it generalizes correctly. Since we are producing the logits as the model output, we need to choose the maximum out of every node and then compare if that predicted class is equal to the data.y. By comparing the predictions one by one, we see that we get 784 out of 1,000 correct. This gives us an accuracy of 78.4%, and this is the end of the first example. For the next example, we will work on a supervised learning dataset called proteins. Let's first handle all the imports. Now let's take a look at our dataset. Our dataset contains 1,113 training examples, and we are given 4 node features, and we have to classify the protein data into 2 classes. To prepare our dataset, we need to first shuffle it. Next, we will have to split our dataset into the training and testing data. This protein dataset is different from the Cora dataset because it contains about 1,000 graphs instead of only 1. To utilize the parallelization for GPU computation, we can use a data loader to concatenate the different graphs into a larger graph, and this will allow the matrix multiplication to be performed together, and hopefully this will speed things up. Now, we will design our graph convolutional network. Similar to the Cora dataset, we need to perform a graph convolution step. However, since we are trying to perform a prediction to label every graph, we need some method to sum up the information that we have for all the nodes. To do so, we will use something called a pooling function, which is called global add pool in PyTorch Geometric. The special thing about our global add pool is that we need to pass in a batch parameter. This is because when we use the data loader to combine the graphs into one big graph, we have an attribute called batch which labels the nodes of the graph and tells us which graph it originally comes from. So when we pass the batch parameter into our global add pool, it will not add the entire batch into one single value. Instead, it will try to retain the batch information for the data loader. Next, we write our model and optimizer. For this example, we will use a training and also a testing function. I will explain it why, but this is not necessary. You can use the training method that you used for example 1. Just as usual, we will return the average loss and the number of graphs that we got the classification correctly. As you can see here, our model is training well and the loss has decreased while the number of graphs that we correctly classified has increased. The reason why I write the testing inside the loop is because for this kind of graph classification task, it seems that the results plateau very quickly after around 10 epochs. So I want to show and prove to you that there is training happening, and so that's why I will output the loss for every 5 epoch. And also, this is also the reason why I chose stochastic gradient descent instead of Atom, because Atom is performing too well and the results are difficult to interpret. And of course, this example is just an overview of what you can do with supervised learning with graph data. For example, you can try other kinds of graph convolution layers, try other number of nodes in the neural network, etc. If you like this video, please like, subscribe, and stay tuned because I will be posting more videos on machine learning and data science. Thank you.